Hi, in this work we present ToolNet using Commonsense Generalization for predicting tool use for robust plan synthesis. I am Rajas Bansal and this is joint work with Sheshturi, Rohan Paul and Mosum at the Indian Institute of Technology, Delhi. Let's consider an example. Imagine a mobile manipulator robot in a household domain asked to perform high-level tasks. The robot needs to interact with many objects with a variety of properties like flatness, shape, material, etc. to complete the task. Thus, the robot needs common sense knowledge about the environment and its objects for task completion. Now, suppose the robot is kept in a new home which can contain new objects the robot has never encountered before. How can the robot generalize the common sense knowledge from earlier environments to completely new objects and scenes? Suppose a robot is given the goal, put fruits in the fridge. There is a lot of knowledge that the human has not specified here, but is essential for completing the task. For example, if there are multiple fruits, a tray might be required for transportation. This is because of the semantic property of flatness of the tray. However, if the tray is not present, the human would improvise with a new object like a box or even a book which is also flat. However, a table cannot be used for the same task because of its weight. Thus, humans innately possess the common sense knowledge about how objects interact with each other and the environment and leverage these properties to complete tasks efficiently. We hypothesize that human demonstrations of these tasks with an existing common sense knowledge corpora like ConceptNet can help us generalize to novel scenes. Prior approaches in the field fall into two categories. One family of approaches consider the problem of learning how to use tools for a goal. We consider the complementary problem of learning the semantic association between tools and tasks, learning high-level knowledge of when tools can be useful. The second category of approaches uses human demonstrated plans to supervise imitation learning models to predict appropriate actions. This work considers a richer space of object interaction such as containment and transport and explicitly models the robot in these domains. To solve the problem of generalization to novel environments, we consider the task of predicting the tool required to complete a task. A tool is an interactable object which is essential for task completion. Current datasets do not contain the complex interactions and data required for generalization to new scenes. Thus, we collect a new dataset of human demonstrations and add conceptual knowledge source like ConceptNet. We train ToolNet, a graph convolution-based imitation learner that generalizes the knowledge from training data to completely new environments. Our ToolNet model predicts a distribution over the tools required for a task given the state and the goal. We crowdsourced a dataset where a human teacher guides a robot simulated using bullet physics engine performing assembly, transport, and fetch tasks. The user interface, shown on the left, was used to collect a total of 1484 plans with 8 different goals per domain and a total of 92 interactable objects. We use home and factory-like domains, shown on the right, with diverse goal specifications to collect various tool interactions and plans for different goals. Let us again consider the goal, put fruits in the fridge. ToolNet casts the environment in the form of a graph, with the objects as nodes and different relations between them as edges. We initialize the nodes with pre-trained ConceptNet embeddings. Thus, if a new unseen object is put into the scene, the model knows about its semantic properties through the embedding. Consider the graph being input to ToolNet. The model uses gated graph convolution to learn an environment-aware embedding of each object. ToolNet combines the semantic and metric embeddings using late fusion. However, all objects may not be equally important. There are some objects which are more important for a particular goal. Thus, we learn attention weights for all objects in the environment and combine them to form a scene embedding. This is then used to predict a likelihood score for every tool in the environment. We show a 35% increase over a simple GGCN baseline for tool prediction. We also show a bigger increase of 55% improvement in generalization. Goal conditioned attention and ConceptNet embeddings compute larger increases in performance. Additionally, we assess the utility of the learnt model in aiding plan synthesis. We use a symbolic planner that uses the predicted tool likelihoods to guide its search. Let us again consider the goal, put fruits in the fridge. This figure illustrates a human demonstrated plan using a tray to transport fruits. In this case, the model has not encountered a box while training. It is then put in a scene which does not contain a tray, wherein it predicts box as a tool. We see a reduction in the effective branching factor by nearly 9 times using predictions of the learned model compared to uninformed plan search. Similarly, as shown here, ToolNet is able to generalize in other domains like factory as well. Thanks for your attention. Our code and dataset is available online.